lines and planes in space is what we're going to talk about now. So the standard, just really quickly, one of the more important things is some of these basic ideas. The standard parameterization of the lines through for the first several problems. This is what's important. There's like 5 of these, but only 4 of them I really think at all would be something you'd be asked about for introduction to all this. But they use the first 4 problems. There are 5 that use this, but we're going to only briefly go over the last one of the 5 that would use this just this directly. But yeah, the standard parameterization of the lines through P0, X0, Y0, Z0 is parallel to, it has this form basically, is T. You probably saw this in calculus too a little bit, some parametric equations. Basically, it's not that complicated here. But basically, we want to find parametric equations for the following lines. First one is lines with a point P of 3, -4, -1 parallel to the vector I plus j plus k. And this is exactly direct use though. You don't have to do any real work here. You just have to mix and match. So what you get is 3 plus t, -4 plus t, and -1 plus t. Of course, t is between -infinity and infinity. Basically, it's greater than -infinity but less than infinity. But basically, the point in green and the vector components in brown, it's 3 from there plus 1 times t, or just t. You could just from I, like these are all going to be just 1 times t because that's what's in front of that's the component of the vector. The component of the vector is just 1 for each of the directions. So -4 and -1 are also they're taken from the point. You're just given point in it's parallel to the vector I plus j plus k, so of course that's how you do it. So the line through P at -2, the point -2, 0, 3, and point 3, 5, -2. Here you just have to form a vector and use one of the points. Well, you can use both of them to show it. You can, if you do some math, you can show that these are exactly the same. These 2 lines will be the same. The equations, the parametric equations are the same, but just to look at it, we'll do both points, and but basically, in this case, -2, 0, and 3, just 5t, because 0 would mean that y0 is 0, so it's not even involved. So I hope you can see, then it's 5i plus 5j minus 5k, 5t, and -5t. And 3, 5, and -2 from 3, 5, -2. 5, 5, -5 from 5, 5, -5. You basically just do that sometimes for these types of problems. It's pretty quickly done like that. So the origin parallel to, this is just like the first one. It's parallel to the vector, to certain vector with a specific point here. 0, 0, 0 is the origin, as you should know. And if we're going to show the work detailed, it's 0 plus 0t equals 0 for x, because there's literally nothing. The vector is 0i technically. But it's all going to be 0 for the x0, y0, or z0 point. And we're going to 1 times t, 2 times t, and 0 times t for the 3 different equations. So yeah, y equals 2t, z equals t, and x equals 0, basically. Parametric equations. The line through 1, 1, 1, parallel to z-axis. A little bit more tricky now. Z-axis has x and y coordinates equal to 0. Vector on z-axis is 0 plus zk. We're just going to say z in general. And the unit vector would be v equals, basically this is based on v equals v divided by the magnitude of v. You could technically split that up into v1, v2, and v3 divided by the individual magnitude of it, the addition of these components. In theory, you could do that, and we do this it's just an illustration of this. But yeah, I mean, obviously these will be 0, 0i and 0j, and just k will have components, which makes sense if you think about the z-axis. It'll just be along k. This line's supposed to be parallel to the z-axis, and it has to go through the point 1, 1, 1, 1. But still, and then you have z divided by zk, which means that's 1k basically. So just k, making sense again. It's parallel to the vector, because the vector just through the z-axis would be k. It's supposed to be parallel to the z-axis. But of course, that means that 1 plus 0t, 1 plus 0t would be y, and z, x and y would be 1 plus 0t both, from the point 1, 1, 1, and 0i, 0j. Okay. Then it's 1 plus t, because it's 1 plus 1 times t. And of course, negative infinity less than t less than infinity. Okay. I would say just skim this one. It's a weird technicality how they do it, but because it's asking you for the lines through 0, -7, 0 perpendicular to the plane. Normally we do this a little bit differently with planes and stuff. You want to find an equation of the plane when you're given a line and stuff, but yeah, we'll just ignore this one. You can look back on it if you really want to. This is kind of how you're supposed to do it. But kind of ignore that last one there. But now it's time for this one. So time for something slightly different. Find equations for the planes in following examples. The plane through P0, which is 0 to -1, normal to this vector, n equals 3i minus 2j minus k. So we use this equation of plane. A times x minus x0 plus b, y minus y0 plus c times z minus z0 equals 0. This is for when you have a vector normal to the plane. Basically, you have a plane going through a point and you have the normal vector to it. In this condition, it's an exact use of it. But yeah. So you just plug into this. And I try to highlight it here, especially with this one. Yeah, the pink goes there and the purple. But it's 3 times x minus 0 plus 2 times y minus 2. The points up P, so 0, 2, and 1. Well, -1, so you add there. And the other part is 3 from 3i minus 2j minus k, so minus 1. Okay, pretty good. So in the end, you get 3x minus 2y minus z equals -3 when it's all simplified down. The next one asks for the plane through these 3 points. So similar to that triangle problem from the last unit or section, you basically take two connected, a, b, and ac. Let's say you have the 3 points connected that way with the vector one way and the vector the other way from the same origin point of a. We just call it a here. I labeled a, b, and c like that and just did a, b, and ac. And I get my two vectors through the normal process we've seen a dozen times at least. And then the vector normal to the plane is the cross product, like in the triangle problem where we're trying to find the area of a triangle. The basic setup's the same. But yeah, cross product, like we've seen many times. I'm not going to be as crazy meticulous at this point because we don't need to take forever going over it. But you should get what I get here. 7i minus 5j minus 4k. And now we use this formula for plane. 1, 1, -1. Trying to close, oh, whatever. You plug in 7, -5, and -4. Those are your A, B, and C. Basically, I don't know if I will explain it, but yeah, basically. A, B, and C are from the vector normal to it, to the plane. Which was, when we got the cross product, that's a vector normal to the plane. And we have the point 1, 1, -1 to plug in for x0, y0, and z0. Simplify down, 7x minus 5y minus 4z equals 6. On the plane through P0, 2, 4, 5, perpendicular to the line. Oh, now we have to kind of go in reverse from our parametric equations, because we're given the parametric equations for this line. And it's basically, this means it's, perpendicular means normal. So normal to line is the vector n equals I plus 3j plus 4k from 1, here it is. 5 plus t, that means 1 times t, 3 times t, and 4 times t, so 3 and 4. 1, 2, 4. So the normal to line will give us that. And it's parametric, I show. So normal to plane is, a equals 1, b equals 3, yeah. I'm over explaining a little here in wording, but that's the first step you do to find the plane. And then it just becomes, using this equation, the 1, 3, and 4 from the normal vector. And of course, the point is 2, 4, 5. So you have minus 2, minus 4, minus 5. X plus 3y plus 4z equals 34. So you get it when you simplify down. Find the plane determined by the intersecting lines, and this one I really wrote out to make sure you understand the process. But it's relatively simple. We have two lines, L1 and L2. I'll label this. In parametric equation form. So we need a point of intersection and a vector normal to plane. The point of intersection is the first thing to find. Once we find these two things, we can write out using that formula that we've been using for planes. The equation of a plane, we equate both lines. So x equals negative 1 plus t, which is equal to 1 minus 4s. You equal both x's to each other, and the y's to each other, and the z's to each other for most things. And solve for t and s. So negative 1 plus t equals 1 minus 4s implies that t equals 2. Because you add 1 to each side, then add 1 to each side, you get 2. T equals 2 minus 4s. So 2 plus t equals 1 plus 2s implies that 2 times t times 2 minus 4s. Or 2 plus 2 minus 4s. The reason for this. So I have t equals 2 minus 4s, you get that. Yeah, 2 plus, so basically I plugged in here. So t plus t equals 1 plus 2s. Yep, from y. The two y's equate each other. That means that 2 plus 2 minus 4s in parentheses, that's the t value, equals 1 plus 2s, which implies that you add 2 and 2 and add 4s to both sides. You get 4 equals 1 plus 2s plus 4s, yeah. I'm simplifying both sides of the equation. From there. Then you get 3 equals 6s, which is, means that s equals 1/2, and t equals 2 minus 4s, which is equal to t. You just solve for t in whatever single equation you want. In this case, I just brought back t equals 2 minus 4s from here and plug in s. So 2 minus 4 times 1/2 equals 2 minus 2, which is equal to 0. And so we have s equals 1/2, t equals 0. Use to solve one set of parametric equations of x, y, z. So I did the t ones with t. So x equals negative 1 plus 0. When t is 0, basically it's negative 1, 2, and 1 plus or minus 0 for both of these equations, depending on which one it is. So you get just negative 1, 2, and 1. So that's the point of intersection, is negative 1, 2, 1. It doesn't matter which you choose, if you choose the t or s ones, because you'll get the same point of intersection here. That's how these work. In the end, it'll all work out. The vector normal to plane we want, you get from the parametric equations, n1 and n2. So, negative 1 plus t, 2 plus t, and 1 minus t. That's I plus j minus k. 1, 1, negative 1 basically is the coefficients in front of them. And negative 4, 2, and negative 2 come from negative 4s plus 2s minus 2s. And the reason we take the cross product because that'll give us a perpendicular vector, a normal vector to it. To n1 cross n2, the two normal vectors, we want what's normal to them. You know, these normal vectors are parallel to these lines. It all works out. You get the cross product, you know, 0i plus 6j plus 6k, which means that a equals 0, b equals 6, c equals 6. When we want, I use our equation of the plane right here, and you just plug in the a, b, c, and the point. Ends up with 6, you know, 6y plus 6c equals 18, but we can simplify that down by dividing by 3 to get c1 in simplest form. So y plus c equals 3. You can easily do it at least. Yeah. Okay, we're getting through this. So now it's just for a couple more examples of stuff now. I'd say basically understanding the equation of a plane and the parametric equations, you know, that would be the main things for this section I'd recommend you learn. Now just for distance, possibly distance, you know, just understand this distance formula, at least for point to the line would be simplest. But d equals the unit p, the cross product divided by magnitude of vector v, no, ps cross v. But so we want to find the distance from the point to the line, 0, 0, 12, and we have parametric equations again right here, as you can tell, 4t, negative 2t, and 2t. Yeah, the line passes through 0, 0, 0 and is parallel. Why did I put 0, 0? I think that should be 0, 0, 12. Just ignore that. Point is what happens here. I'm just trying to write it out again. But its point is it's parallel to that. Distance formula, of course, I'll just explain now. PS. So obviously it's just going to be in k from how this looks. So it'll be just 12k basically. It'll be the only thing that matters from it. We have to have 0, 0i and 0j, you know, for your cross product. And v, that's what you get v from this 4t, negative 2t, and 2t. And ps is just yeah, wait, no, 0, 0. Yeah, whatever. Oh, right. So 0, 0, 0 is right, because that's what we're subtracting. Sorry if it's a little confusing, the work here. But how you know 0, 0, 0 is because the parametric equations here. Going to the line. There's no, it's just 4t, negative 2t, and 2t. There's no plus to it, you know, there's no other term. So that means its origin, 0, 0, 0. And that's why it's easy math. The ps is just, you subtract, you know, your point you're given from the point to the line. You know, the point comes as a second thing, ps. S is the point in this problem type. And so the cross product, of course, is done for ps cross v, given these calculated ps value and the v from the line. 24i plus 48j. ps cross v, you go to this process, you know, the magnitude of it, of course, is the square root of the squared of the components added together. And v is the same way. So 24 square root of 5 divided by square root of 24. And 24 square root of 5 divided by square root of 24 is just square root of 24 times square root of 5. It makes sense when you think about it, because it's like 24 to the 1 power divided by 24 to the 1/2 power would mean 1 minus 1/2. 24 to the 1 minus 1/2 power, you know. If you really want to be technical, so it's 24 to 1/2 some, which is just square root. Eventually you simplify down to 2 square root of 30, and that's the distance. Now distance from the point to the plane. Instead of a line, we have a plane. In this one, we have the point 2, negative 3, 4 in this plane equation. And it's a little bit different of a formula. D equals PS times n divided by magnitude of n. This is the dot product, of course. So it's the magnitude of this whole thing. Just to prevent negative numbers, of course, I assume. But still. But then n equals I plus 2j plus 2k. We get that from this formula x plus 2y plus 2z. 1, 2, 2. And the magnitude of it is just 1 squared plus 2 squared plus 2 squared, which square root of all that equals 3. So we already got n in the magnitude of n. So PS, we take s to be 2, negative 3, 4 at a point given, and use intercepts of x plus 2y plus 2z equals 13 to figure out what point to use for p. In this case, I use 13, 0, and 0 because, yeah, basically you make 2 of them equal to 0 if you can, and the other one equal to what you need to get the right hand side, so you only have one non-zero number if possible. That's what I did, 13, 0, 0. Then it's 2 minus 13i plus negative 3 minus 0j plus 4 minus 0k. You get negative 11i minus 3j plus 4k. And the d is equal to that this thingamabobber. Yeah. Technically it's a unit vector because of the form of it. But so it's 1/3 times, you basically end up like that, like we've done this many times before. It all simplifies down. I hope you can follow on to 3. So the distance is 3 in the end. Find the angles between the planes x plus y equals 1 and 2x plus y minus 2z, that's what it is, equals 2. So the two planes is just an angle between normal vectors of both. And you use this old formula, say it equals the inverse cosine of n1 dot n2 divided by the magnitudes of n1 and n2. So yeah, you should recognize this from 12.3 on dot product. You see, this is why dot product and cross product are very important. If you understand those sections, you can't go wrong. Out of this first chapter specifically, a lot of it. Very commonly occurring and not too hard to remember a couple formulas things. But okay, the angle is going to be given by this. So n1 and n2, n1 is I plus j plus 0k because it's x plus y equals 1. You don't have even the z term there. Then it's 2 plus, 2i plus j minus 2k from 2x plus y minus 2z. And the magnitudes are given right here. n1 is equal to square root of 1 squared plus 1 squared, which is equal to square root of 2, and this square root of 9 equals 3 in the end, for 2 plus I, 2i plus j minus 2k. So we have square root of 2 times 3 on the bottom, but it won't matter because, well, it will for this one. It's going to simplify nicely. We'll get an exact number and then let's see what the angle will be. So it's I plus j plus 0k times 2, dot 2i plus j minus 2k. So 1 times 2 plus 1 times 1 plus 0 times negative 2. So that's 2 plus 1, which equals 3, divided by 3 square root of 2. Which is 1 divided by square root of 2, so it's the inverse cosine of just that. Which I changed to square root of 2 over 2, the same thing, I rationalized it. And that's the form I learned it in pre-calc for the unit circle. So I know that's exactly pi fourths radians. So the angle between them is pi fourths radians. Square root of 2 over 2 is exactly on it. But that's just how I would do it. If you know 1 over square root of 2, then fine, do it right away. But I learned square root of 2 over 2 is equal to pi fourths for the inverse cosine or inverse sine. exactly. And finally, find the point in which the line meets the plane. We already kind of did this. We're just finding a point of intersection. Because that's what's given, the line meets plane. We know it intersects the plane, so I have 1 and 2 I added in for these, labeling them. You just plug in 1 minus t, 3t, and 1 plus t into the formula for the plane. These parametric equations. And solve for t. And then you plug t into x, y, and z to get the points, the coordinate. So 2 times 1 minus t minus 3t plus 3 times 1 plus t. In pink, I tried to make it obvious what substitute in. And you get 5 minus 2t equals 6 in the end, which implies that 2t equals negative 1, which is t equals negative 1/2 now. It's negative 1 divided by 2. So x equals 1 plus 1/2, which equals 3/2, and you have negative 3/2 for y from 3 minus it. Or 3 times negative 1/2. And z is 1 plus negative 1/2, which equals 1/2. So that's where the line meets the plane. We did this already for a longer one, where to do this is just a prerequisite to get to the point. So overall, just don't overstress these types of problems. Just look through them, and there's a couple important problems here. A couple formulas to know. Some recurring ones, some new. Particularly how to use the distance formula, but also, more importantly, how to know those vectors parallel